Good afternoon, everyone. I'm Jie Hao from Florida State University, and today I'm going to talk about our recent work, modeling recurrence for transformer. And this is the joint work with Xing Wang, Baosong Yang, Longyue Wang, Jinfeng Zhang, and Zhaopeng Tu. So the outline includes motivation, approach, experiment, and conclusion. So the transformer model based solely on the attention mechanism has been the state of the art across the language pairs. And both encoder and decoder have n-identical layers. But however, recent study revealed that the lack of recurrence hinders transformer further improvement of translation capacity. And moreover, modeling recurrence is crucial for capturing several essential properties of input sequence, such as hierarchical structures. So starting from these findings, we introduce an recurrence encoder into the conventional transformer model, the right one. And the recurrence encoder reads the word embedding of the source words and outputs a sequence of hidden states which embeds the recurrent information. And similar to transformer encoder, it has a stack of n identical layers. Each of layer has two sublayers. The first one is the recurrence modeling, neural network, and a recurrent modeling network, and the second one is fully connected feed-forward network. And I will introduce the recurrence modeling first. So for the recurrence modeling, one intuitive choice is recurrent neural network. And here in this work, we implement the bidirectional GRU as the RN part. And I will not talk too much about this model. And furthermore, we extend the recurrent neural network by recurring a set of feature vectors by a set of feature vectors extracted with the attention model, the bottom one, and we named it attentive recurrent neural network, which allows the model to learn a global and abstract feature vectors over the input sequence. And specifically, the ARN performs T recurrent steps on the attentive output of the input representation HR-1. And here the ARN can be extended to the bidirectional variant. And the number of recurrent step T is allowed to be unequal to the length of input sequence J. And since the output of recurrence encoder unnecessarily shares the same length with the transformer encoder, so the combination strategy on the encoder side, such as concatenation, is not an universal solution in this scenario. So we feed this recurrence information directly into the decoder side. And in detail, we use additional attention layer to perform the attention on the recurrent representation. And the first strategy to integrating the recurrence representation into the transformer is gated sum. So in this strategy, it can combine the two outputs of the attention sublayers in a gating fusion. Here, the lambda n is an interpolating weight calculated by a logistic sigmoid function. And another strategy is named stack. So the the decoder first attends the output of transformer encoder, and the attention output serves as a query to attend the output of recurrence encoder. And actually, several previous work have shown that the shortcut for gradient backpropagation benefits language modeling. So in this work, we implement the shortest path as the recurrence encoder has a single layer and its output directly feed into the top of decoder layer. And here the two pictures shows that two strategy of integrating into transformer, the gated sum and the stack. And let's look at the experiment part. So we conduct experiment on WMT14 English to German translation task. And first we investigate the effect of recurrence modeling with a stack fusion. So from the plot we can see that introducing recurrence encoder consistently improves the performance in terms of the blue score, and the bi-ARN model outperforms bi-RN model, the yellow one and the green one. And concerning all the bi-ARN models, reducing the layers of the bi-ARN can consistently improve the performance. The last three models you can see. So these findings confirm that the shortcut effect. And moreover, we also investigate the effect of integration strategies. And here we have two observations from the plot. The first is that feeding to only top layer of decoder outperforms feeding to all layers of decoder. And the second observation is that the stack strategy marginally better than the gated sum strategy. So actually, this the first finding also reconfirms the shortcut effect. So in the main results part, we use the single layer bi-ARN feed to top layer of decoder with a stack strategy as the default setting. We conduct the experiments on WMT14 English to German and WMT17 Chinese to English. So from the two plots, we can see that the proposed model consistently improves the performance for the translation quality, and across the model variants, base and big, and language pairs, English to German and Chinese to English. We also conduct some analysis for the proposed model. First, we investigate the effect of recurrent steps for the single layer bi-ARN model. And from the plot, we can see that the blue score goes up with the increase of recurrent step. However, the trend does not hold when the recurrent step achieve 8. So this demonstrates that it is necessary for to be in recurrence for the ARN model. And we also conduct some linguistic probing tasks proposed by the Facebook AI, and there are 10 probing tasks proposed to study what linguistic properties are captured by the encoders. So actually, each probing task is a classification problems which focus on a single linguistic property. And we can split the 10 probing task into 3 groups: the surface, syntactic, and semantic. So from the table, we can see that from the table, the last 3 rows show that the proposed AIN model can capture the deeper linguistic properties, including the syntactic and semantic features. And moreover, the single layer by AIN is better achieve the best performance on the syntactic properties. This also verifies that the argument at the very beginning I just mentioned, modeling recurrence can capture some special linguistic properties like syntactic structure. So this study demonstrates the necessity and effectiveness of the modeling recurrence for transformer, and we introduce a novel attentive recurrent network as well as RNN, and the 2 integration strategies into transformer. And our approach benefits from a shortcut on gradient backpropagation. Okay, thank you for listening. Questions are welcome. Thank you.
Questions?
Hi, thanks very much. I'm Juan from Facebook. So how much slower is the training time?
How much what?
The training time, does it change?
Yes, actually it's I can show you for the 6 layers encoder, it's there is the slowest training time, but when the encoder's layer decrease to the single layer, actually the training time is not slow too much. Actually, in our paper, I have reported the training time. You can, if you want to see the detail, you can refer my paper. Yeah.
Thanks for the talk. I was wondering if you can comment on the differences between your approach and the universal transformers. They also try to tackle the problem of modeling recurrence for the transformer.
Yes, you mean the differences?
Yeah.
Yeah, actually, our paper aims to directly introduce the recurrence into the transformer, and our paper aims to just simply show that some straightforward recurrence model can benefit the transformer, but not explore the whole space of the recurrence encoding. But the universal transformer, I think, actually their motivation is not same of us, because they actually they want to make a strong transformer baseline to I think to a universal scenario. I think, yeah.
No more question? If not, let's thank the speaker and all the speakers for the session, as well as Bashar Al-Hafni, who has been live tweeting the entire session. So you can go back to Twitter and read the details and comment there if you like. Thank you.